Hello students, today we will be taking up a topic solid state. Some of the portions regarding the packing efficiency was left, so we would like you to cover that. So I will do the recap also for what we have done already. We have taken up solid state, and under solid state we have discussed some of the areas like the type of solids basically. And the characteristics of solids, we know that solids are having definite mass, volume, shape. That we have done from 6th class onwards, we are aware of that. So therefore we are not given any focus. So main focus was amorphous and crystalline solids. We have done the different type, like quartz is a type of amorphous solid. Okay, so means to say that crystalline solid and amorphous solid, we have done certain definite difference between that: melting point, cleavage, heat of fusion, anisotropy, and this was the most important, like amorphous are isotropic in nature. Okay, and the short range order and long range order is also one of the area. Now if we talk of further index questions, you can do yourself. And the classification, under that classification we are having molecular solids like we can say HCl, HBr, HI, H2, chlorine. So that are of two types, like polar and non-polar. If you talk of HCl, that is polar. If you talk of H2, Cl2, because this is a gas. When we are decreasing the temperature, it will change to liquid, and if you again decrease the temperature, then it will turn solids. This is the point, hydrogen bonded. So these are all under molecular solids. And one more is their covalent network solid and ionic solids. So ionic solids, you know that ionic forces are there, ions between ions, metal ions are there. So metal ions means positive charge kernels and negative charge electrons, which you are done in +1 bonding chapter also. Covalent or network solids, so like silicon dioxide is there, diamond is there. So then these are the characteristic of this all the solids. So in molecular solids, constituent particles are molecules, and ionic solid constituent particles are ions, metallics are positive charge kernels and negative charge electrons. Similarly, covalent network solids consist of atoms like silicon dioxide, quartz, diamond. So these are some of the questions you can try yourself. And next is crystal lattice and unit cell. As I have earlier discussed, this red portion composed of unit cell, and the green portion combined is repeated again and again. That is called space lattice or crystal lattice. So there the points are known as lattice points, and it's also known as Bravais lattice, and these are having parameters A, B, C, the lengths on y-axis, x-axis and z-axis, and the angles alpha, beta, gamma between the axis. And after that we have discussed about the different unit cells like simple, cubic, body centered and face centered. So and that also different crystal systems we have discussed, 7 different crystal systems, which is most symmetrical is cubic and which is most unsymmetrical is triclinic. And further to that we have discussed about the different crystal system based on the factors, parameters A, B, C and alpha, beta, gamma with the examples. And under each cubic crystal system or any tetrahedral system, there are further unit cells are various. They are like primitive, body centered, face centered. Okay. So similarly, rhombohedral we are having primitive one. So this composed of all these 7 crystal systems. Under that, unit cell may be 3 or 4 type or 2 type or 1 type. So these are the types of unit cell. So primitive, body centered, face centered, primitive and body centers. Okay, so one is cubic and another might not be cubic. This is the meaning why we have shown others altogether. Okay. So now the next is upper syllabus point of view. Always the question will be asked on cubic unit cells. Nothing they will ask about tetrahedral. They will not ask for rhombohedral or anything or triclinic. They will ask only for cubic unit cell because which is most symmetrical. And under that also you should know that how to calculate the Z value. So in the last video I have told you also number of contribution at the corner will be 1/8, and total number of atoms required to make one unit cell is 1/8 into 8 is equal to 1. So this you have done in previously class also. Body centered 1/8 into 8 plus 1, that is equal to 2. Similarly face centered 1/8 into 8 plus 1/2 into 6 is equal to 3. So then next is now this topic we have to take up. This topic is related to packing. So packing is the topic we have discussed now. So in this you see we have to arrange atoms. Now you take balls, like a various balls you can take, and just to start arranging them in the layer. If one layer you can arrange, and you can arrange in the second layer. So if you see, just wait for 1 minute, like you can see here, the arrangement of spheres. Arrangement of spheres would be in one dimension. One dimension would be there, this single layer, closed packing of sphere in one dimension. If you put one more layer, like for example, you just think of your room, and on one corner you start filling this atoms or balls, sphere that you are filling. If you full-fledged complete your floor, that is known as two dimension. This is one dimension. If you cover two full-fledged floor, then it is two dimensions. So which axes are there? We have covered two axes in that direction. That is two-dimensional packing. So now, if we are keeping the, now what is there? Now if you want to keep one more layer over it, for example, you have kept the atoms in one layer. If you want to keep it over it, either the one thing is that you can keep over the same, like we can see that the same atoms can be again put up on the other. Now here they have told you the concept of voids. When you combine the atom, there will be space between the atoms. That is called void. And void basically are of two types, tetrahedral void and octahedral voids. Okay, so please, so let us talk about the voids. In this voids, what is there? You just think of four atoms. Four atoms means four balls. You just bring close that balls. Okay, there would be, if you take the center of the atom and join that four balls altogether, their tetrahedron will be formed. So that tetrahedron is called void. Tetrahedral void. Because here in the, if you see from the screen, you are not able to find out what I want to say. But exactly that is the point. That four atoms when joined together and that void is formed, that is called tetrahedral void. Similarly, octahedral void, if three atoms are joined together and over that three more atoms, like for example triangular form, you join these three atoms, okay, and vertex is in the direction like north. If you join these three atoms joined together as in the form of triangle, and one vertex is on the north side, now keep three atoms in the form of triangle, but the vertex is opposite in the south. So now the void which is formed by joining these six atoms, that is called octahedral void. This is the meaning of tetrahedral and octahedral voids. Okay, so now this is there. This concept you just keep in mind only, nothing else, because some things are there. It is very difficult to make you understand it practically. I have to show you the animations and from the extra marks. Now you are having the link for the extra marks also. So you can just check their animation in regards to voids particularly. Number of octahedral voids always double. Number of octahedral, if it is n, the tetrahedral void will be doubled. And now packing in the third layer. We have not just discussed about the third layer. We have discussed only the two layers. That is two-dimensional packing. Okay. If line is there, only one line is there, that is one dimension. If a floor is there, then two dimension. And if above that we are keeping the atom, that is called three dimension. I will make you understand in a very easy manner of this three-dimensional packing. Like ABC and ABAB, two types of packing we are having. So if you see from the figure 1.18, we are having two types of packing, AB and ABC type of packings. And now in this case, you just imagine that you are sitting in the class and sender student is surrounded by 6 students. So this portion, A portion, you can see from the diagram here, 1.18, in the center atom is surrounded by 6 atoms. Now what is there? You just imagine this situation. The center atom is there and 6 surrounding atom is there. Now if you think that I have to place 3 atoms above it in the form of upper triangular voids or lower triangular voids, vertex is in one direction, that's 3. Now it means the center atom was joined with the 6 atoms in one plane, and above the plane 3 atoms, so total 9. If again, now you just understood that one atom is surrounded by 6, and above that 3 more are there. You just think that 3 more is there at the bottom of the 6. Don't see whatever I am explaining you in 1.8, 1.18. Now if you see the figure 1.18, there are 6 atoms in the red, like above that B is there, above that A is there. Now you just take A, means the one A is in the end, at the end, and one A is in the middle. So you take middle one, and above that you check B is there, and below also B is there. So A B packing. This packing is one of the packing that is called. If A, B and C packing is there, type triangle is changed. So that type of packing is called cubic closed packing. So I would like to tell you once more. Center atom is there, surrounded by 6 atoms, 3 above, 3 below. If above and below are in the same vertices, is same direction, like north, that is called AB packing. Now if center atom is there, surrounded by 6 atoms, above and below, 3 atoms are there, that is vertices are in the opposite direction, that is called cubic closed packing, and also known as face centered packing, face centered cubic unit cell. So this coordination number for both cases is 12. Normally what question they will ask is, what is the coordination number in cubic closed packing? Your answer is 12. What is the coordination number of hexagonal closed packing? That is 12. AB type of packing is which type? Hexagonal. ABC type packing is which type? Cubic closed packing. These are the questions being asked for the last 5 year or 6 year, 10 year. So that only you need to focus. Okay, so now there is one question in regard to the number of atoms. Now you have understood that this question always student finding it typical, but whatever you can understand, you just understand it. Here the concept is used is number of tetrahedral voids is equal to double the number of octahedral voids. If you have seen previously, number of tetrahedral void is double the number of octahedral voids, and number of octahedral voids is equal to number of atoms. This is the concept being used in the numericals. Okay, how it is applicable, just let us see how we can do that. So in this area, if compound is formed by 2 elements X and Y, A atoms has occupied the anionic side, that is Y, and makes CCP, cubic closed packing, like ABC packing, and the element X as cation, and occupy all octahedral voids. X is occupying octahedral voids. Now, what is the formula of the cation? Now in this you know that octahedral voids is equal to number of atom Y present, and all octahedral voids Y occupied by X, and their number would be equal to number of elements of Y. The atoms would be XY. So I feel that you may not understand it, but I think whatever you just see that second problem, it will be helpful to you. Atoms of element B form hexagonal closed packing lattice, and those of element A occupy 2/3 of tetrahedral voids. Now, as earlier I have explained, the concept of number of tetrahedral voids is equal to 2 times the number of octahedral voids. Now we have to take that tetrahedral void is equal to 2 times the number of elements of B. A is occupying tetrahedral void and B is occupying, let us say, X. Okay, now if B is occupying X, and then tetrahedral would be 2/3x. Tetrahedral voids here, A occupy 2/3 of tetrahedral voids. Now if B is X, A would be 2x, and A would be equal to 2/3 into X. Okay, so means to say that what I want to say is B is occupying octahedral voids, and you know that octahedral voids is equal to number of atoms n. And if n I am taking or x I am taking, that is one the same thing. So if B is equal to x, then they are telling that A is equal to 2/3 of tetrahedral voids, and tetrahedral voids is 2n, As per the formula, tetrahedral is 2 into number of octahedral voids. Octahedral voids are occupied by B, and then A would be 2 by 3 of 2x. So it means 4 by 3 x is to x. So it would be A4B3. So you need not to worry much. If you are not able to understand this question also, we will make you understand when our classes will resume. That's not a piece important information, and moreover important question also not. If you last see 2, 3 years, 4 years, 5 years, no question is being asked in that. Okay, so this topic you just read the location of tetrahedral and octahedral void. I am not going to take up. I will complete the rest portion, which is as far as important, and mostly question may be asked from that. So okay, so now packing efficiency. Packing efficiency derivations we will do in the class. Now you just see that what we are going to take up. The packing efficiency, 3 factors. Last time I have discussed with you. For SCC it is 52.4, and for BCC it is 64, and for FCC is 74. These are the 3 factor derivations we will do in the class. That's not a problem, because derivation as such not coming in the exam, but we will do that. That's not a problem. Okay, so 52, 68 and 74. 52.4, 68 and 74%, that are the packing efficiency. Packing efficiency means percentage of solid space in a unit cell. And now calculations of Z we have discussed already. Density is equal to Z into M divided by A cube divided by Avogadro number. And further to that, we are having this numericals we have done already. So I am not going to take up. You have to do practice. Okay. And next is this is all about the topic whatever we have done. So I would like to, up to this portion you just complete. Next I will take up further imperfections in solid, the next topic. Okay, I would like to repeat whatever I have told you. I have told only the basic thing, that of like if the packings are of 3 types, that 1 dimensional, 2 dimensional and 3 dimensions. So basically we need to cover up 3 dimensional packing. First, second you can do, but mostly questions will be asked from 3 dimensional packing. And 3 dimensional packing are of 2 types. One is hexagonal closed packing and one is cubic closed packing. In hexagonal closed packing, AB type of packing is there. AB type of packing means the center atom is surrounded by 6 and 3 atoms are below and 3 above. If 3 atoms whatever below and above is the same vertices in the same direction, that is called AB type of packing. If ABC packing or cubic closed packing, then we are saying, because center atom is surrounded by 6 atoms and 3 below and 3 above, but the above is, the vertex is in the opposite direction. Okay, so if one vertex is in the north direction, another vertex is in the south direction. So that is in both cases coordination number is 12 and packing efficiency is 74%. So this was all about the packing efficiencies, and you need to do the numericals. I think that's all for today, and tomorrow we will take up the imperfections in solid. Thank you.